Let's begin our introduction to the chemistry of alkenes by examining 5 common addition reactions. These addition reactions are hydrohalogenation, hydration, halogenation, halohydrogen formation, and oxymercuration. The common theme of all these reactions is that in all of these reactions, an electrophile will be added to the alkene. So this molecule which gets added will be an electrophile. So why it needs to be an electrophile? The reason is the presence of these pi electrons on our alkene makes our alkene electron rich. So electron rich means that this alkene is a nucleophile. Or in other words, our alkene is an electron source. And as we learned that nucleophiles seek to donate electrons to a species which lacks electron, and that species is electrophile. So therefore, in all these reactions, an electrophile will get added across the double bond. A double bond will break. Let me use different colors. A double bond will break open, or pi bond will break, and our electrophile will get added across the carbon-carbon double bond. Hence, all of these reactions are known as electrophilic addition reactions. Now, as you can guess here, that in case of hydrohalogenation, our electrophile will be HCl, HBr, HI. In hydration, electrophile is water, and so on. So all of these species which we will use for addition are electrophiles, and our alkenes will be a nucleophile. So therefore, a characteristic pattern of the mechanism of each of these reactions will be that will make a bond between a nucleophile and an electrophile. In next sections, we will investigate each of these reactions in detail. We will see what products are obtained when these electrophiles are added to any alkene. We will also understand and learn the mechanism of each of these reactions, and we will also see if there is a characteristic pattern of addition, or in other words, is this addition random? Can A or B, can they be added to any of these carbon, or is it a specific location where the A will go or where the B will go? So all of those questions will be answered in the next few slides. Let's start the electrophilic addition reactions of alkenes by investigating addition of hydrogen halides. The hydrogen halides such as HCl, HBr, or HI add to alkenes to give alkyl halides. These reactions are carried out in pure reagents such as pure HCl, pure HBr, or pure HI, or it can also be carried out in presence of a polar solvent such as acetic acid. Let's take an example of addition of HBr to propene. Now, as we saw in previous slide, that all of these electrophilic addition reactions take place in such a way that this pi bond will break and HBr will get added across the carbon-carbon double bond. In other words, H and Br bond will break, the pi bond will break, one side of the pi bond will get hydrogen, the other side gets Br. Now, earlier we said that there is a chance that this addition may be random or it may be selective. Let's take a look at products. So there are two possibilities of products. In one possibility is that hydrogen gets added to carbon number 1, that's number 8, and Br gets added to carbon number 2. In that case, the resulting product will be 2-bromopropane. The other possibility is that hydrogen gets added to carbon number 2 and Br gets added to carbon number 1. So this is the product uh, shown here. As it turns out that the addition of Br to carbon number 1 is not observed. So that means that addition of hydrogen halides to double bond is not random. It means it is selective. So these kind of selectivity in which any species is selective towards any region of a molecule is known as regioselective. So hence this reaction is a regioselective reaction. So the definition of regioselective reaction is that an addition or substitution reaction in which one product is formed in preference to all others. The regioselectivity of this reaction was known by or first noted by a Russian scientist named Vladimir Markovnikov. So Markovnikov, after investigating many of these kind of reactions, he generalized a rule, or he came up with a generalization, and that generalization is known as Markovnikov's rule. So according to Markovnikov's rule, in the addition of hydrogen halide to an alkene, hydrogen adds to the double bonded carbon that has greater number of hydrogens already bonded to it. So in other words, the hydrogen will go to that carbon which has more number of hydrogens already bonded. So that's why hydrogen in this reaction prefers carbon number 1 because it has more hydrogens already bonded. So this rule is known as Markovnikov's rule. It should be noted that Markovnikov's rule is applicable to only asymmetrical alkenes. Now, asymmetrical alkenes are those alkenes who have different number of hydrogen atoms bonded to the carbon-carbon double bond. For example, in case of 2-butene, if you look at the number of carbon atoms across the double bond, they are same. So these kind of alkenes are known as symmetrical alkenes. In case of symmetrical alkenes, Markovnikov's rule is not applicable because they have same number of hydrogen atom. So in this case, if we perform addition of HBr, the end product will be same. Doesn't matter which side hydrogen goes or which side Br goes. We will always get the same product, and the product will be two bromo butane. So regardless of the region where hydrogen or Br goes, the product will always be the same. It will be 2-bromo butane. Let's take a look at the mechanism of this reaction. In step number 1, there will be a new bond formation between a nucleophile and an electrophile. And remember, I mentioned that I call this step as nuke attack. And in this reaction, the pi electron act as a electron source. So therefore, our alkene is a nucleophile in this case. So alkene will attack the electrophile. So electrophile is HBr, or HBr is the electron sink. So alkene is the electron source and HBr is the electron sink. So these pi electrons, they attack the hydrogen. Now why would they attack hydrogen? Because remember, this is a nucleophile, and nucleophile likes the nucleus. Nucleus means positive charge. Now you may say, oh, there is no positive charge. Yeah, but there is. The reason is because of the high electronegativity of bromine or bromide ion. Bromide is partially negative and hydrogen is partially positive, and that partial positive charge on hydrogen is enough to attract the attack by the nucleophilic alkene. So this nucleophile will attack the hydrogen in order to preserve the duet um, valence shell around the hydrogen. So this sigma bond will move and those electrons will jump to bromine atom. Okay, so this step will be a slow step, and as we know from the kinetics that slow steps are the rate determining step. And after this attack we will get a reaction intermediate, and this intermediate will be a carbocation. Now because pi electrons are used or have been used to make the bond, therefore this carbon will get a positive charge, and of course there will be a new bonded hydrogen atom. And we will get a bromide ion. So this will be our first step of reaction mechanism. In step number 2, our newly formed nucleophile bromide ion, as you can see, bromide have plenty of extra electrons, so therefore now bromide is a nucleophile. So this newly formed nucleophile will like to donate its extra electrons to another electrophile or another electron sink. So that electron sink is the carbocation. And so this positive charge on the carbon act as the electrophilic site. So therefore this will be a fast reaction because both of the nucleophile and electrophile are extremely unstable, and after making the bond they are going to be relatively stable molecule. So therefore this step is a fast step, and we know that fast step is not a rate determining step. The end product, if it is a chiral compound, it will always result in a racemic mixture. So for example, in this case, this will be a racemic mixture. Now, reason why it will be a racemic mixture, because the likelihood of this attack on the top side is same as from the bottom side. So it means that excuse me, let me correct it. So as I was saying, that the likelihood of attack on top of this electrophilic side or the bottom is same. So 50% chance that it may attack on the top side and 50% chance may attack at the from the bottom side. So that's why we get 50-50 mixture of R and S stereoisomers. So that's why we get a racemic mixture. So as we learned in previous slide, that step 1 of electrophilic addition reaction mechanism involves the formation of carbocations. Now, carbocations are a species in which carbon atom has only 6 electrons in its valence shell and it bears a positive charge. For example, this is an example of a carbocation. Now, carbocations are classified as primary, secondary, or tertiary depending on how many carbons the charge carrying atom is bonded to. For example, in this example, the charge carrying carbon atom is bonded to only one more carbon, so therefore this is an example of primary carbocation. Now, in case the charge carrying carbon atom is bonded to two carbon atoms, such as shown here, this will be an example of a secondary carbocation. And finally, if the charge carrying carbon atom is bonded to three carbon atoms, in this case, the carbocation intermediate is known as a tertiary carbocation. All carbocations have 6 valence electrons around the carbon atom with positive charge. Therefore, they are all electrophiles, and they all act as a electron sink in reaction mechanisms. Because of lack of electrons, they all act as Lewis acids. The bond angles around the carbon atom with positive charge is 120 degrees. That's because the carbon atom has only 3 bonding units around it. So for example, in this case, only 3 bonding sites. So from VSEPR theory, we know that any atom with only 3 bonding sites around it has a trigonal planar structure. So therefore, carbocations have trigonal planar structure with 120-degree bond angle. The carbon with the carbocation, they have sp2 hybrid orbitals, and the unhybridized 2b orbital lies perpendicular to the sigma bond framework and it contains no electrons. The structure of a carbocation is shown in the next slide. The structure of a tertiary carbocation is shown here. So this is a tertiary butyl carbocation, and as we can see, the charge bearing carbon atom is bonded to 3 other carbon atoms, so therefore it's a tertiary carbocation. In a carbocation, the carbon bearing the positive charge is bonded to 3 sides, so therefore as predicted by VSEPR theory, the structure or geometry of the carbocation is trigonal planar as shown here in this structure, and the approximate bond angles are 120 degrees. According to the orbital hybridization model, the electron deficient carbon, this one, uses sp2 hybrid orbitals to form sigma bonds. So in case of carbon-carbon sigma bonds, it uses the sp2 and sp3 hybrid orbital overlap to form these bonds, and the vacant 2p orbital is lying perpendicular to the plane of the carbon-carbon sigma bond network. this p orbital is vacant because it's a carbocation, it has lost its electron. We have already defined primary, secondary, and tertiary carbocations. There's another kind of carbocation in which the charge-bearing carbon atom is not bonded to any other carbon atom. So this kind of carbocation is known as methyl cation. From the experimental evidences, it has been found that the tertiary carbocation is the most stable carbocation, and the methyl carbocation is the least stable. And the order of carbocation stability is shown here. So secondary is second in stability, and primary carbocation is third in stability, and methyl carbocation is the least stable. In fact, methyl and primary carbocations are so unstable that they are never observed in solution because their lifespan is extremely short. Now that we know the order of stability of carbocations, how do we account for this order? As we saw during the discussion of anion stability, a system bearing a charge is more stable if the charge is delocalized. It means if the charge is spread over multiple atoms, then the system is more stable. We can apply the same logic to the stability of carbocations. Let's consider the example of a tertiary carbocation as shown here. Using the principle of delocalization of charge, we can explain the order of stability of carbocations if we assume that alkyl groups bonded to positively charged carbon atoms release electron density towards the carbon and thereby help delocalize the positive charge. So these alkyl groups, they release electron density. Now, how do they release electron density? The positive charge on the carbon atom polarizes the electrons adjacent sigma bonds. So this positive charge attracts the electrons in these sigma bonds. Now these carbon atoms are, because they are further connected to hydrogen atoms, so overall all of these electron density will be delocalized towards the positive charge of the carbocation, and thus the carbocation is delocalized over nearby atoms, because when the electron density is donated to the carbocation atom, so these carbon atoms assume a slight positive charge as shown in this electron density map. So this creation of slight positive charge results in delocalization of a positive charge. In other words, this positive charge gets spread over multiple carbon atoms, and thus because the same charge is shared by multiple carbon atoms, overall the system becomes more stable. So as in tertiary carbocations, the charge-bearing carbon atom is bonded to three carbon atoms, so the delocalization is spread over multiple or more carbon atoms. In case of methyl or primary, there aren't that many carbon atoms bonded to the charge-bearing carbon atom, so therefore the delocalization cannot take place, and hence methyl and primary carbocations are not that stable. So this effect of releasing the electron density to stabilize the charge-bearing carbon atom is known as inductive effect. So the order of stability of carbocations can be explained with the help of inductive effect. An energy diagram of addition of hydrogen bromide to 2-butene is shown here. This line represents the energy of reactants. Our reactants are 2-butene and HBr. As we remember, the first step involves the attack of nucleophile. In this case, the nucleophile is our alkene, and alkene attacks the electrophile HBr, and it's a slow step, or in other words, it's a rate determining step. It is slow step because the system is going from relatively stable molecules to form a reaction intermediate. And as we remember, the intermediate was a secondary carbocation. Although secondary carbocation has some stability, but as compared to the reactants, the energy of carbocation is still pretty high, so this is relatively unstable molecule. In order to go from reactant to intermediate, our system has to cross an activation barrier. That's a significant amount of energy. That's why the first step is a slow step, because not all collisions will result in crossing of this barrier. But once this first barrier or first transition state is crossed, and now we have a carbocation intermediate. Now carbocation intermediate can either go back to reactants, or it can cross another barrier forward direction, and it can result in product. In both cases, the barrier to cross is relatively small. It's not very high because the energy of carbocation is already high, so this amount of extra energy is not that high. Now, because our products are at lower energy level than our reactant, so therefore this product represents more stable state. So therefore the reaction intermediate preferentially moves forward, or the second step, and it gives the formation of product. Now, because products are at lower energy level than the reactant, so this extra amount of energy is released, so therefore this reaction is exergonic reaction. So now that we know the stability of carbocations, let's look at the regioselectivity of addition reactions one more time in case of asymmetrical alkene. So this is the first reaction we saw in the addition reactions, and we said that the 1-bromopropane is not observed. So this is not the product which we obtain when we conduct this addition reaction. So let's understand why 1-bromopropane does not form. The answer to this question can be obtained from the mechanism of this reaction. So as we know that the first step of this mechanism is the attack of nucleophile. So let's do that. So in step number 1, the pi electron attack the positively charged proton, and it would result in the formation of a carbocation. Now there are two possibilities. One possibility is that carbocation is formed such that the hydrogen atom goes to carbon number 1. Let's number it 1, 2, and 3. So possibility number 1 is when the hydrogen goes to carbon number 1. So in that case, we would obtain this carbocation. And as you can see, this is a secondary carbocation. In both possibilities, we will get a bromide ion. I'm not going to write that because it's common. Yeah, let's write that too. And there will be a bromide ion. Now, possibility number 2 is that when the hydrogen goes to carbon number 2. So let's look at what kind of carbocation we get in this case. Right, as we can see in possibility number 2, the carbocation formed is primary, and from the order of stability of carbocations, we know that primary carbocations are not stable. So hence possibility number 2 does not uh, form, or in other words, because of the low stability of primary carbocation, the possibility number 2 does not even exist. So only reaction intermediate which does exist is the secondary carbocation. So secondary carbocation is such that the hydrogen goes to carbon number 1. So step 2 is just fast step. In this step 2, carbocation is already formed. We already have the next nucleophile, which is our bromide ion. So in step number 2, the already formed carbocation act as a electrophile, and the bromide act as a nucleophile. And the end product is the 2-bromoprotein propane. So now from this mechanism and the stability of carbocation, we understand why 1-bromoprotein propane does not form. So this explains the regioselectivity of addition reactions. And this is why Markovnikov's rule always states that uh, that when we add hydrogen halides, the hydrogen of electrophile goes to the carbon atom, which already contains more number of hydrogen atom. When Markovnikov proposed this rule, the mechanism of this reaction was not established. He proposed this rule only based on the results. He did not know the reason behind it, but now we know. Addition of water to alkene is known as hydration reaction. Water is added to alkenes as HOH, which means is that hydrogen from water will add to one carbon, and OH from water will be added to other carbon atom of the carbon-carbon double bond. Hydration of alkene is an important reaction to produce alcohol. So this reaction is a way to synthesize alcohols. Addition of water is accomplished in presence of an acid catalyzed. The most common acid to be used in this reaction is sulfuric acid, but any other reaction will also work. This reaction is also regioselective, and HOH or water adds in accordance with Markovnikov's rule, which means that the hydrogen from water will be added to that carbon of double bond which already contains more hydrogen. So in other words, this hydrogen will go to this carbon atom because it contains more hydrogen, and of course OH will go to the other carbon atom. So therefore the product of addition of water in presence of sulfuric acid to propene is 2-propanol. Similarly, in the second example, uh, the addition of water to 2-methylpropene, the hydrogen again will go to carbon number 1 because it contains more hydrogen. and the resulting product will be 2-methyl-2-propanol. The mechanism of acid-catalyzed hydration of alkenes is quite similar to what we already proposed for addition of hydrogen halides. As we know, this reaction is catalyzed by sulfuric acid. In other words, sulfuric acid acts as a catalyst. The role of sulfuric acid is to convert water into hydronium ions, because hydronium ion is much better electrophile than plain water. So in presence of any acid, water absorbs a proton and it gives rise to formation of hydronium ion. Now the step 1 of mechanism is again same as the mechanism of hydrogen halide. It's a nucleophilic attack or nuke attack. Alkene again act as a nucleophile. So as we are taking example of hydration of propene, so let's draw the mechanism of this reaction. So first step is nucleophilic attack. Propene or alkene act as a nucleophile, and the water or hydronium ion act as an electrophile. So the positive charge on oxygen will pull these electrons towards itself, so making hydrogen even more acidic. So therefore it is more susceptible for nucleophilic attack. Again, this step is a slow step, hence it's a rate determining step, and it will give rise to formation of a carbocation intermediate. And as we know that again there are two chances or two types of carbocations which may be formed, but because we know the stability of secondary carbocation is higher, therefore hydrogen from water goes to the carbon atom with more number of hydrogen atoms, that is carbon number 1. This is because this addition will give rise to formation of secondary carbocation, and we know secondary carbocation is more stable carbocation. And plus will produce a water molecule. In the second step, a nucleophile, which is water now, will attack the newly formed carbocation, because carbocation now act as an electrophile. The oxygen atom in water has two lone pair of electrons, and these lone pair of electrons act as a nucleophilic source, and the carbocation act as a sink. So this will be the attack of nucleophile again, and this will produce a complex, and this reaction will be fast because carbocation already has a high energy, so the activation barrier is not that high, and it would result in formation of a species, and this species is known as an oxonium ion. In oxonium ion, oxygen has a positive charge, so this is oxonium ion. And oxonium ion is not a stable molecule, so the last step will be a transfer of proton. So in the final step, the oxonium ion will lose a proton. That's a loss of proton step. So in order to take a proton away, we need a base, because that would be an acid base, so transfer of proton. So in this case, water act as a base. This will also be a fast step, and the resulting compound will be an alcohol. Plus hydronium ion. So as you can see, we started with hydronium ion, and the hydronium ion is generated back at the end. So that's an indication of a true catalyst, that hydronium ion or the acid is not used in the reaction. So it is just a catalyst. In some electrophilic addition reactions to alkenes, we observe formation of unexpected products. For example, in case of a alkene shown here is 3,3-dimethyl 1-butene. If we add HBr to this alkene, the addition of HBr would take place according to Markovnikov's rule, and the expected product will be the addition across the double bond. So we would expect to see two bromo 3,3-dimethyl 1-butene. However, when the actual experiment was done, it was found that less than 20% product was this expected product. So this was minor product. On the other hand, major product was something else. It was unexpected. So major product in this case was this product, or major product was 2-bromo 2,3-dimethyl butane. Is butane. So about 80% or more than 80% was this unexpected product. So the formation of this unexpected product can be explained with the help of a concept called carbocation rearrangements. In electrophilic addition reactions to alkene, there is a possibility for rearrangement if a carbocation is involved. Now, what is rearrangement? Rearrangement is a change in connectivity of atoms in a product compared with the connectivity of the same atoms in the starting material. So, for example, if you notice, this methyl group did not exist at this carbon atom. What happened is that this methyl group was present at this position, but it moved. So this is a rearrangement. To understand the origin of this rearrangement, we need to look at the reaction mechanism. Here is another example of an addition reaction in which we observe carbocation rearrangement. According to Markovnikov's rule, the expected result from this reaction should be the formation of 3-methyl 2-butanol, or in other words, the hydrogen should go to number 1 carbon and OH should go to number 2 carbon. However, this formation is not observed, or even if it's observed, is the minor product. Major product is 2-methyl 2-butanol, in which OH is added to a carbon atom which was not even part of the carbon-carbon double bond. So let's now take a look at the reaction mechanism, and then we will be able to understand why a rearrangement takes place. To explain carbocation rearrangement, we will take a look at the reaction of 1-methyl 1-butene with HCl. It is an electrophilic addition reaction, and the mechanism proceeds as we explained in the case of hydrohalogenation. So the first step involves the attack of nucleophile, and we know that alkene act as a nucleophile and hydrogen halide act as a electrophile. So first step, the pi electron attack the proton, so that's a nuke attack as we know, and it results in formation of a carbocation, and according to Markovnikov's rule, hydrogen goes to the carbon atom which contains more hydrogen, so therefore this hydrogen goes to carbon number 1, and this will result in formation of a secondary carbocation, and we know that secondary carbocation is more stable than primary, so that will be the first step. In normal circumstances, this step will be followed by a second step, and in second step our newly formed nucleophile will attack the newly formed electrophile and we will get the product. That will happen in most cases. However, in certain reactions, this step does not take place. Instead, a rearrangement takes place. Now, why would a rearrangement would take place? So let me explain. So this step does not take place. So this carbocation is a secondary carbocation, and we know that although secondary is stable, but tertiary is more stable than secondary. So if by rearranging some sigma bonds, I'll explain which one it does rearrange or which one can be rearranged. If a secondary carbocation can be converted to tertiary, then the rearrangement will lead to a more stable intermediate. So let's take a look at this carbocation. So in this carbocation, if we look at it, the carbon which carries the positive charge right next to that carbon, that's so we're gonna call this at number 1 carbon for the sake of simplicity. So number 1 carbon is the carbon which carries the carries the positive charge. If the neighboring carbon has a proton or a methyl group, either a proton or a methyl group, and that proton or methyl group can be shifted to the carbon atom. Can be shifted. The emphasis is on can be. I'll explain why it will be and why it will not be in a little while. So this shift is known as 1,2 shift. So we're gonna call the carbon atom which contains the positive charge 1 and the neighboring will of course be 2. So that's why the shift is known as 1,2 shift. So after this shift, the proton which was connected to the neighboring carbon will go to the carbon atom which has a positive charge. In doing so, now this carbon has its octet complete, so positive charge is gone from here. However, the neighboring carbon gets a positive charge. But there's a difference. Although we still have a carbocation, so we start with a carbocation and we end up with a carbocation. But there's a difference. We started with a secondary carbocation and we ended up with a tertiary carbocation. So now the key part, why this mechanism or why this rearrangement will take place. This rearrangement will only take place if a less stable secondary carbocation has a chance to improve to more stable tertiary carbocation. This will not be possible in all carbocations. In those cases where this improvement from secondary to tertiary is not possible, then the rearrangement will not take place. Only in those cases when 1,2 shift lead to a more stable carbocation, then 1,2 shift will take place. And in that case, now we can see that the positive charge has shifted to the neighboring carbocation. And so therefore the final step, which is the attack of the newly formed nucleophile, instead of taking place at this position, so that does not take place anymore because the secondary carbocation doesn't exist. So this step will take place at the newly formed tertiary carbocation, which will result in formation of the new product. So once the carbocation rearrangement generates the more stable intermediate, then the final step will take place in which the nucleophile chloride ion attacks the carbocation, which is an electrophile, to give us the product. Remember, carbocation rearrangement will take place in only those reactions where a less stable intermediate has a chance to form a more stable intermediate. For example, if I'm performing this reaction in case of propene, so in this case our intermediate is a secondary carbocation. However, from the neighboring carbon, let me just expand this one. In this case, even if this shift here, let's for the sake of argument, let's say that the shift does take place in this case also. So after the 1,2 shift, now we have a primary carbocation, which is horrible because we went from secondary to primary. So that's never going to happen. So this will never take place. So whenever you draw the reaction intermediate, always see if there is a chance for 1,2 shift, and after doing 1,2 shift, if the secondary improves to tertiary, then go ahead and do the carbocation rearrangement. But if by performing 1,2 shift our intermediate gets worse, for example secondary changes to primary, that's bad. Or even if a secondary stays secondary, even in that case the rearrangement will not take place. It only takes place if our intermediate improves its stability. Both chlorine and bromine react with alkenes at room temperature. The product of this addition reaction is a dibromo or dichloroalkane. Fluorine also show the addition reaction with the alkenes, but the reaction is extremely fast and is hard to control. Therefore, it does not have any uh, use at lab conditions. The addition of iodine is extremely slow, and therefore iodine addition is also generally not carried out in organic labs. This reaction is also known as halogenation of alkenes, and halogenation is usually carried out with either pure halogens or in presence of an inert solvent such as dichloromethane. The addition of bromine or chlorine to cycloalkenes gives a trans dihalo product, and it will be a racemic mixture. At first glance, these two trans dibromo products look like the same molecule, but there is no plane of symmetry, so therefore they are mirror images of each other, hence they are enantiomers. We will discuss the stereochemistry of this addition reaction in detail in another section at the end of this chapter, but for now, just remember that this addition reaction occurs with anti-stereoselectivity. Now, what's the meaning of anti-stereoselectivity? So, anti-stereoselectivity is seen in those reactions in which the addition reaction takes place such that one of the atom adds from the top of the sigma bond plane, and the other atom gets added at the bottom. Or in other words, both halogen atoms add from the opposite face of the double bond. So the end product will have a stereochemistry similar to trans positions, but cis and trans does not exist in normal alkenes, so therefore we can't really call them cis and trans. So therefore this kind of addition is known as anti stereoselectivity addition. Let's take a look at the reaction mechanism of addition of halogens to alkene. In this case, we'll take an example of addition of bromine to an alkene. As usual, the first step is the attack of nucleophile, and in this mechanism step, a new bond between the nucleophile and the electrophile will be created. Now we know that alkenes act as a source of electrons, hence they are nucleophiles, so therefore bromine will act as an electrophile. So let's draw the mechanism. So this carbon-carbon double bond represents our alkene. So in step number 1, alkene attacks the bromine and this attack will lead to formation of a bridged uh, product which is known as brominium ion intermediate. Now remember, after the pi bond is broken down, these carbons uh, they have a tetrahedral geometry now. So therefore we represent the tetrahedral geometry with these wedges and dashed bonds. This brominium ion is resonance stabilized, and the resonance structures are shown here. The brominium ion has three resonance stabilized structures, so let me draw all three. Okay, so these are the three contributing resonating structure. And out of these three structures, the first two structures are the major contributors, and the the third structure is the structure which is responsible for retaining the geometry of this brominium ion. I'll explain what's the meaning of retaining the geometry in next slide. Although it looks a little odd with the bromine atom with a positive charge, but nevertheless it's an accepted Lewis structure, and molecular modeling calculations have shown the presence of a positive charge on bromine. So this is an accepted resonance contributing structure of brominium ion. Now in this step, not only a brominium ion is generated, the second bromine atom, this one, is also produced. So this bromine atom will act as a nucleophile in next step. Now next step, as we know, is the attack of nucleophile to newly generated electrophile. So our brominium ion has a positive charge on it, so brominium ion act as a electrophile. So this is the electrophile. The meaning of retaining the geometry is that this contributing structure is the one which explains the formation of trans product. As we can see that the top side of the double bond has already a bridged brominium cation, right? So it means the top side is pretty much blocked for the nucleophile to come and attack these carbon atoms. So these carbon atoms are already bonded on the top side. So only side which is available for this electrophile to attack is from the bottom. So now in the next step, this bromine nucleophile will attack from the bottom. So when it attacks from the bottom, of course the product will be trans, because we already have one bromide atom on the top. The second one will be connected to the bottom. Now again, we can see that there are two carbon atoms where the nucleophile can attack, and both carbon atom has some positive charge. And so the likelihood of this electrophilic addition to happen on either of these carbon atom is 50-50. So therefore, in the next step, this bromide nucleophile has equal probability of attacking either this carbon atom or that carbon atom. So that's why we see the two stereoisomers which will form in this reaction. So in step number 2, the nucleophile, which is bromide ion, attacks from the bottom because top side is already covered or already blocked by the brominium bridged cation. So as I stated in previous slide, that the likelihood of bromide to attack either on this carbon or the second carbon is equal. So therefore we get 50% product in which the geometry is either R and another 50% is the product in which S. So in other words, it's a racemic mixture. Now this kind of arrangement in which one atom attacks from the top side and the other atom is added to the bottom side is known as anti-coplanar orientation. The Newman projection of this anti-coplanar orientation is shown here, and as we can see in the Newman projection, one of the bromide unit is on the top side and the other one is at the bottom, and these two are the stereoisomers of each other. The addition of chlorine or bromine to cyclohexene and its derivative gives a trans-diaxial product, as we can see here. Because this addition also proceeds through the brominium ion mechanism, so therefore one of the bromine atom will be added on the top of the double bond and the other one will be added to the bottom. As we can see that both of these positions are axial positions, so that's why this kind of addition reaction is known as trans-diaxial addition, because it will lead to a diaxial product. Now two stereoisomers which will form are shown here, and from chapter number 4 we know that the trans positions are not favored. Now cyclohexene can go from one chair conformation to other chair, and when the chair flips, the axial positions become equatorial, and we know that equatorial positions are more stable. So therefore, although this reaction will produce a trans-diaxial addition product in the beginning, but because of the stability, this chair form will flip into the other chair form in which the diaxial bonds will convert to equatorial positions. Now, because the original brominium ion can form on either face of the double bond with equal probability, as shown here, so 50% this one and 50% the second stereoisomer, both trans enantiomers are formed, so therefore our product is a racemic mixture. Treating an alkene with the bromine or chlorine gas in presence of water results in addition of hydroxyl group and halogen group to the carbon-carbon double bond, and this reaction forms a product called halohydrin. A halohydrin is a compound containing hydroxyl group and a halogen atom on adjacent carbons. The one which contain hydroxyl group and bromine on adjacent carbons are known as bromohydrins, and then those compounds which contain chloro group and hydroxyl group are called chlorohydrins. An example of a halohydrin reaction is shown here. In this reaction, propene reacts with the chlorine gas in presence of water to form 1-chloro-2-propanol, which is a chlorohydrin. This reaction is regioselective, and in this reaction halogen add to less substituted carbon atom, or in other words, halogen adds to those carbon atom which contains more hydrogen. So this carbon is known as less substituted carbon atom. And hydroxyl group adds to more substituted carbon atom. The addition of halohydrin to alkenes is not only regioselective, but it is also anti-stereoselective. Both the regioselectivity and anti-stereoselectivity are illustrated by the addition of HOBr to 1-methylcyclopentene as shown in this reaction. Bromine and hydroxyl group in this reaction add anti to each other, with bromine bonding to the less substituted carbon and hydroxyl group bonding to the more substituted carbon. Less substituted carbon has more hydrogens attached to it. So this is evident from the products shown here in this reaction. To account for the regioselectivity and anti-stereoselectivity, chemists propose a three-step reaction mechanism which is shown in the next slide. The step 1 of halohydrin reaction mechanism is similar to step 1 of halogenation reaction. In this step, a new bond between nucleophile and electrophile is formed. As we saw earlier, our alkene act as a nucleophile and bromine act as an electrophile. This nucleophilic attack will give rise to a bridged brominium ion intermediate. As we saw earlier, that this intermediate is resonance stabilized and it has three resonating structures, or three contributing structures. Now the first contributing structure, this one, it has a positive charge on a carbon atom which is secondary in nature. So hence it is a secondary carbocation. And we know that secondary carbocations are relatively stable carbocations. So therefore this resonating structure is a major contributing structure. In the second structure, we have a bridged brominium ion, and this bridged brominium ion plays important role to maintain the geometry or stereoselectivity of the reaction. Now the third structure shown here, as we can see that in this structure, positive charge is present on a primary carbon. So therefore this is a primary carbocation, and we know that primary carbocations are not very stable, so therefore this structure plays very little role. The step 2 of this mechanism is the attack of nucleophile, which is water in this case, on the more substituted carbon. This attack will open the ring structure and it will form an anti-addition product. And in the third step, the proton is transferred from the oxonium ion by a base. In this reaction, water acts as a base, so proton is transferred to give rise to halohydrin, and as we can see that the product formed here is an anti-stereoselective product. Anti means that one of the addition group is on one side of the double bond and the other group is present on the other side of the carbon-carbon double bond. The important point in this reaction mechanism is the attack of nucleophile in step number 2 to more substituted carbon atom. At first glance, this looks like counterintuitive because why would a nucleophile attack at more sterically hindered carbon? That doesn't look right. Um, in fact, it appears that the attack to the other carbon would be more easy because it has only hydrogen, so it's more space is available. However, experimentally, it has been found that in step number 2, the nucleophile attacks on the more substituted carbon atom of the bridged intermediate. So this carbon. This preferential attack at more substituted carbon atom can be explained by a combination of two factors working together, and those factors are listed in the following slide. The preferential attack of water in step number 2 of this reaction mechanism on the more substituted carbon of the bridged brominium intermediate can be explained with the help of electrostatic potential map as shown here. It is evident from this map that the carbon and halogen bond to the more substituted carbon is longer than the one with the less substituted carbon. Because of this difference in bond length, the transition state uh, for the ring opening can be reached more easily. So the longer bond, so this bromine is already away from this carbon. So if our nucleophile attack here, so this longer bond can be easily broken down. So therefore, that explains why the attack on the more substituted carbon is more easy. Secondly, it is also evident that the more substituted uh, carbon has more positive charge around it as shown by the blue color, so which represents the lack of electron density around it. We can also recall that alkyl group stabilized carbocation uh, in the resonance contributing structure was more stable, or it was more contributing structure. So therefore, there is a more positive character on the carbon atom which is present at the more substituted uh, corner of the bridged brominium intermediate. So because of these factors, nucleophile attacks the more substituted carbon, and hence this reaction is anti-stereoselective as well as regioselective. Oxymercuration reduction reaction is another method to convert alkenes into alcohols. So we can say that this is another kind of hydration reaction. So this hydration of an alkene can be accomplished by treating it with mercury 2 acetate and water as shown by this reaction. The product of this reaction will be an organomercury compound. The subsequent reduction of this organomercury compound by using a reducing agent named sodium borohydride will result in formation of an alcohol. As we can see in this reaction, the end product or end alcohol is similar to the one which was obtained by the addition of water in presence of acid catalyst. So we can say that the result of oxymercuration followed by sodium borohydride reduction is Markovnikov's addition of HOH. All additions are called Markovnikov's addition if the hydrogen part goes to the carbon atom which contains more hydrogen. So as we can see that the end product in this reaction also results in a product in which hydrogen goes to the more uh, uh, to the carbon with more hydrogens. Therefore, this addition is also known as Markovnikov's addition. At this point, you may think that we already have a method to convert alkenes to alcohols, that is by addition of water in presence of acid catalyst. Then why do we even need oxymercuration reduction reaction? This is because of an important feature of this reaction. The feature is that oxymercuration reduction reaction occurs without rearrangement, which is unlike acid-catalyzed addition of waters to alkene. For example, if we perform oxymercuration addition reaction to this alkene, that is 3,3-dimethyl-1-butene, the product will be simple Markovnikov's addition in which the OH group is added to the carbon of the double bond with less number of hydrogens, and hydrogen will be added to the carbon atom which contains more number of hydrogens. So this is simple Markovnikov's addition product. We call it Markovnikov's product. On the other hand, if we perform same reaction or if we use same alkene and try to perform the hydration in presence of acid catalyst, the major product will be the one where rearrangement will take place, and the product will be this one. So if you want to perform a simple Markovnikov's addition to those alkenes where there is a chance of rearrangement, then oxymercuration reduction reaction is the only option. This reaction occurs with anti-stereoselectivity. So that is, if we perform oxymercuration reaction to cyclo or cycloalkenes, the OH group will be added on one side and hydrogen will be added on the opposite side. The fact that the oxymercuration reduction reaction is both regioselective as well as stereoselective, therefore chemists have proposed a reaction mechanism which is closely analogous to the one for the addition of halogens to alkenes. Another important thing to note is that the absence of any rearrangement in this reaction also suggests that at no point during this reaction a free carbocation is formed, because if a free carbocation is there, then rearrangement must take place. The absence of rearrangement indicates that free carbocations are not involved in this reaction mechanism. Let's analyze and try to understand the mechanism of oxymercuration reduction reaction. The step 1 of this reaction involves the dissociation of mercury to acetate to produce an electrophile. In step 2, a new bond between a nucleophile and an electrophile is generated. As in case of other reactions, our alkene acts as a nucleophile and the mercury electrophile, which was generated in step 1, is the sink for the nucleophilic attack. The result is a formation of an cyclic intermediate. This intermediate closely resembles the bridged brominium ion intermediate which we saw in halogenation reaction. However, in the bridged intermediate, so this bridged intermediate is known as the bridged mercurinium ion intermediate. In this intermediate, the two pi electrons of the carbon-carbon double bond form a ring containing 3 atoms bonded to 2 electrons, as shown here. So the dotted 3 bonds are a special kind of a bond. So it's a 3 atom bonded with only 2 electrons. So this open cation structure with the positive charge on the secondary uh, carbon, which is shown here, is a minor contributor to the resonance hybrid. The open cation structure in which the positive charge is on the primary carbon is even smaller contributing structure. So this structure has a negligible contribution towards the resonance hybrid. The major contributor is the bridged mercurinium ion. Now, because both the carbocation uh, resonance contributors have negligible contributions, therefore this reaction does not involve any rearrangements. In step 3, anti-attack of water, which act as a nucleophile on the bridged mercurinium ion intermediate, occurs at more substituted carbon atom to open the three-membered ring. The proton transfer from this oxonium ion to water completes this oxymercuration reaction. So this will give rise to the oxymercuration product. We account for the regioselectivity of oxymercuration reaction, that is the attack of water nucleophile on more substituted carbon atom, exactly the same way we accounted for in case of halogenation reaction. Of the two carbon atoms in the bridged three-membered ring intermediate, the more substituted carbon has a greater degree of partial positive charge and hence it is attacked by the nucleophile water. In addition, computer modeling indicates that the carbon-mercury bond is to the more substituted carbon of the bridged mercurinium ion intermediate is longer. So this side of bond is longer, just as in case of halogenation reaction. So therefore, longer bond is easier to break. So hence, this results in anti-addition of water nucleophile. Step 4 is the reduction of carbon-mercury bond to convert it to carbon-hydrogen bond. The reducing agent which is used in this reaction is sodium borohydride. The mechanism of this reduction process is beyond the scope of this book and hence it will not be discussed in this chapter. Just like oxymercuration and reduction reaction, hydroboration oxidation reaction also have two parts. In first part, hydroboration reaction takes place, and in second part, oxidation of the product of hydroboration will take place. The net reaction from hydroboration and subsequent oxidation of alkene is the hydration of carbon-carbon double bond. For example, if we start with an alkene and in first step we conduct hydroboration, which is done with the help of a borane, and followed by oxidation. Oxidation is conducted by using hydrogen peroxide in presence of sodium hydroxide. The resulting product will also be an alcohol. But there is an important difference. The difference is that in this case, if you can see, the OH group is added to the carbon with more hydrogens, and hydrogen is added to the carbon with less hydrogens. So in other words, hydroboration followed by oxidation is a technique in which an alcohol is formed, but this alcohol is opposite of Markovnikov's addition product. In both the reactions studied earlier, which were oxymercuration followed by reduction, as well as hydration in presence of acid catalyst, the product were anti-Markovnikov's addition. But this one is opposite of those. So this product is known as a non-Markovnikov's addition product. Just to give you an example, so that we can compare, if we start with the same alkene and we use either water in presence of sulfuric acid, or we use oxymercuration reduction reaction, either one of those, the resulting product will be an alcohol where OH group is at second carbon. But in case of hydroboration and followed by oxidation, the OH group is at number 1 carbon. So that's an important distinction. So that's where hydroboration followed by oxidation, the reaction becomes so important, because this is the only method to convert alkenes into non-Markovnikov's alcohols. As we mentioned that this reaction has two parts. In first part, hydroboration takes place. Hydroboration is the addition of borane to an alkene to form trialkyl borane. So borane, one borane is added to 3 alkene molecules, and this reaction actually takes place in 3 steps. In step number 1, one of the BH bond will break, and so what we can say is that one of the hydrogen goes here and rest of the molecule is added here. It's not the mechanism, I'm just pointing out what's happening. So it's an addition of borane to alkene takes place, and the same step is repeated 3 times or 2 more times, because borane has 2 more B and H bonds, and eventually when 3 alkene molecules are added, so we get a trialkyl borane product. Boranes cannot be prepared as a pure compound because it dimerizes to diborane, and diborane is a toxic gas which ignites spontaneously in air. However, borane forms stable Lewis acid-base complex with ethers. One of the commonly used ether is tetrahydrofuran. So the complex of borane with tetrahydrofuran is commercially available, and this complex is used as a source for hydroboration reaction. The hydroboration reaction is both regioselective as well as stereoselective. Regioselective means the boron binds to less substituted carbon atom, and the stereoselectivity of hydroboration reaction is opposite of oxymercuration. In this case, it is added to the same site. So both hydrogen and boron compounds are added to the same site. So this kind of stereoselectivity is known as syn addition. It is opposite of anti. In the hydroboration part of the reaction, concerted regioselective and syn stereoselective addition of boron and hydrogen to the carbon-carbon double bond takes place in the first step. The meaning of concerted regioselective and syn stereoselective is that during this addition process, the molecule orient in such a way that hydrogen uh, is oriented toward the inner side of alkene and boron is oriented towards the outer side of the alkene. This is because boron is a larger atom than hydrogen, and because of the steric repulsions between the alkene chain and the boron, these steric repulsions orient the borane molecule in such a way that boron atom is closer to the first or less substituted carbon atom, and hydrogen is oriented towards the more substituted carbon atom. So this accounts for the regioselectivity of this reaction. Now, because both hydrogen and boron are present on the same side of the molecule, hence the addition takes place on the same side. So this kind of addition is known as syn addition. It is opposite of the addition which we observed earlier, and that addition was anti-addition. So anyway, so this hydroboration part is the one where regioselectivity and stereoselectivity choices are made. So once hydrogen and boron are added to the alkene, the pi bond breaks, and hydrogen and boron atoms are added to the alkene. So this step is repeated 2 more times, and it gives rise to a trialkyl borane. Now, trialkyl boranes are oxidized with the hydrogen peroxide and sodium hydroxide, and the product will be an alcohol, and in this alcohol the OH group will be present at the carbon atom, which has more hydrogens present on it. So this alcohol will be a non-Markovnikov's addition product. Let's write the reaction mechanism of hydroboration oxidation reaction. We'll take an example of an alkene such as 2-methyl propene, and we know that hydroboration oxidation reaction of this alkene will generate an alcohol. So let's write the product, and then we will try to understand the mechanism. So in this reaction, the first part is the hydroboration part, and then the second part is the oxidation part. The end product of this reaction will be a formation of an alcohol, and in this case the OH will be added to the less substituted carbon, and hydrogen will be added to more substituted carbon, and both hydrogen and OH group will be present on the same side, so that's why it's called syn addition. So this will be the product. Now let's write the mechanism. So in mechanism, the first part is hydroboration. So in hydroboration, alkenes react with borane. And as we saw earlier, because of the steric repulsion, the borane stays away from the more substituted part. So this side is the more substituted side. So borane is on the other end of the alkene, and hydrogen is oriented towards the more substituted, and so this will be the orientation of our borane, and that's all because of the steric repulsions. Now at this time, a rearrangement, not really rearrangement, but the bonds will form, and it will lead to addition of boron and hydrogen to alkene. The pi bond will break and there will be new hydrogen atom at more substituted carbon and boron substituent at less substituted carbon. Now as we can see, we have two more B and H bonds, so this step will be repeated two more times. And we will end up getting a tri-substituted boron. So in tri-substituted boron, it would look something like this product. I'm not showing the hydrogen parts because it's in bond line structure, it's unnecessary to show this hydrogen. But if you really want to show, the hydrogens will be on this side. It's not important to show these hydrogens, so I'm going to omit these hydrogens. For the next step, I'm going to call this big alkyl chains as R groups, because it's not possible for me to draw these bulky alkyl chains multiple times. So I'm just gonna call these groups R groups. So therefore this product of hydroboration reaction will be represented by this molecule. The second part of hydroboration oxidation reaction is the oxidation. So now let's take a look at what is the mechanism of oxidation part of this reaction. In the oxidation reaction, which comes after the hydroboration step, the hydrogen peroxide reacts with hydroxyl group from sodium hydroxide, and this reaction will generate a nucleophile and this nucleophile is known as it's known as hydroperoxide ion. So this is called hydroperoxide ion. Plus water. In step number 2, hydroperoxide ion attacks the trialkyl borane, which was the product from hydroboration step. Now, as we can see that trialkyl borane is an electrophile because boron atom has only 6 valence electrons around it. So only 6 valence electrons. So therefore it is electron deficient. On the other hand, hydroperoxide is electron rich. So it's a nucleophile. So this will result in a nucleophilic attack, and the product of this attack will be a complex between hydroperoxide and the trialkyl borane. This step is followed by a rearrangement. In this rearrangement, the alkyl group moves from the boron to oxygen, and the hydroxide group leaves. Minus hydroxide means this hydroxyl group is leaving, and the resulting species will be this complex. Now step 2 is repeated 3 times. And once it is repeated 3 times, we will get a trialkoxyborane. In trialkoxyborane, all alkyl groups are connected to oxygens, and oxygens are connected to borane. So this is a species, and it's called trialkoxyborane. In the final step, the trialkoxyborane reacts with the sodium hydroxide to produce 3 molecules of alcohol and sodium borate. So this is the reaction mechanism of hydroboration oxidation reaction.